What's up? It's time for some more physics with Mr. Simpson. Yesterday we looked at standing waves and we came up with a formula to explain how the wavelength of a standing wave relates to the length of the string that it's on. That looks like this. And so the wavelength of the standing wave was equal to twice the length divided by an integer, and the integers go up 1, 2, 3, 4. We will see a pattern where they don't go up 1, 2, 3, 4 pretty shortly. And these standing waves are created when something continuously is sending waves down the string, and they hit the other end and reflect off that end and go back towards the source of the incoming waves. And the interference of the new waves and the reflected waves is what causes standing waves in the first place. And regions where there is constructive interference are known as antinodes. Regions where there is destructive interference are known as nodes. When you're looking at this standing wave pattern, usually they happen so fast that you kind of just see it, and it doesn't really look like it's changing. And that's why it's called a standing wave. If you think about the video where the professor was shaking the spring, he never did it all that well. But when you create a good standing wave, the nodes and the antinodes are not moving around. It just kind of looks like one static thing. Hence the name standing wave. So we looked at the situation when both ends of the string are fixed in place. So you get patterns that look like this, or one node in the middle like this, or two nodes in the middle like this. That's not the only possible scenario for standing waves. You could have a situation where one end is fixed in place and the other end is free to move up and down. And in those, this is one fixed, one free end. In these situations, the fixed end will be a node and the free end will be an antinode, because there's no other way for the standing wave to form if a node is not at the fixed end and an antinode is not at the free end. So once you draw these patterns once, they're easy to draw again, but coming up with them in the first place is a little hard. So if the string is fixed between these two lines, let's say this length is L, like it was yesterday, there will be a node here, so we know the string starts here, and there will be an antinode on this end. And the simplest way to connect a node and an antinode is to just go straight up like that. And so that's where the string would be at one extreme, and at the other extreme it would be down here. And that's a little bizarre to imagine. So let me see if I can cause that to happen in all right, fixed end, loose end, no damping, oscillate. So that's way too much frequency. Let's start with a really low frequency. Restart. Okay, so with a really small frequency, you get something like this. It's not quite the standing wave pattern that we're talking about yet, I don't think. Let's see, it probably needs more. Probably going to edit this out. Alright, this is close to what I'm talking about. Do you see how the amplitude of these oscillations just kind of took off and they went crazy? Like a while ago it was only going up and down a little, and now it's just flying up and down. And yeah, this end is moving a little bit. So it's not truly technically a node right here, but it's moving a lot less than the other end. And because it just stopped and got all messed up, that tells me that I didn't actually find the exact right frequency for this standing wave pattern. I'm close. When you see the oscillations just really take off like that, that means you're close to a standing wave pattern. And in practice, I have a little vibrator oscillator like this that you can attach a string to, that we normally do this in class, and we change the frequency up and down until we decide, okay, yeah, now that's a standing wave pattern. The way that you find one is when the amplitude just goes crazy and blows up like this. Because if I decrease the frequency just a little bit, the oscillations will immediately not be as large. Oh, I lied. They're still pretty big. Go down more. Okay, anyway, this is roughly what that standing wave pattern would look like. One end fixed, even though this is moving slightly, and the other end just going crazy up and down. But you see how there's no other nodes in the middle that aren't moving? It's the whole string is going up, and then all the way down, and then all the way up. That's what this first pattern looks like in practice. And so the next most complicated, or the next simplest pattern to draw is one where there is one node out here in the middle, like this. And so you have an antinode right here, you have a node right here, you have an antinode, you have a node. I didn't draw them on the first pattern, but on the first pattern there's a node, antinode. You can probably guess what the next pattern is. You just add another node. So that looks something like this. And you could keep going with it. The next one would have 3 nodes. Probably don't need any more than that. The key thing about all of these is there's a node on the left, there's an antinode on the right, and there's whatever in between. So let's look at these and imagine that we're looking at an actual wave, not a standing wave. If we were looking at a wave, you got to think about what fraction of the wave are you looking at. So it goes up, it hits a peak, then if this were like a normal sine wave, it would go back down, and then it would go back up again, right? So we're not even looking at half of the wave pattern. Half of the wave pattern would be over here. We're looking at a quarter of the wave pattern. It just goes up. That's 1/4 of the full wave pattern. So it's hard to read this blue. Let's go with the green. 1/4 lambda equals L is the relationship between the wavelength here and the length between the ends of the string. The next pattern down, this section is half of a wavelength, and then this section is 1/4 of a wavelength. So you got a half plus a quarter. So 3/4 lambda equals L. And it's easy to count these patterns if you remember that one antinode lobe like this is half a wavelength, and then this is half of that, so 1/4. Here we have one full wavelength plus another quarter. So 5/4 of lambda equals L. Here we have one full wavelength plus a half plus a quarter. So that's 4/4 plus 2/4 plus 1/4 is 7/4. And you might see the pattern now. The number on top is increasing by 2 every time, or the numbers on top are all odd. So if I put an n there, this could work if n is only the odd numbers. And that's That's probably not the pattern you would come up with if I said write down a pattern for this, but that's the way it's commonly written in physics textbooks. And then the other thing is this is usually solved for lambda. So if we solve it for lambda, it's 4 times L over N. Put a box, and remember that N is odd. This is the relationship between lambda and length of the medium. If one end is fixed and one end is free. All right, there's only one more scenario, and it's kind of absurd, but it's useful when we go to talk about air columns. And an air column, think about an organ, the musical instrument, an organ. It's just a bunch of pipes that you blow air in, and the length of the pipe controls what pitch of sound or what frequency of sound it makes. And so that is literally an air column that sound waves travel through and create standing waves in. You need the next thing we're going to talk about to describe an air column. But you'd be hard pressed to find an example of this scenario with a string, because it's pretty impossible to set it up. So this would be 2 free ends. The standing wave pattern in a string where both ends are free would imply that you need to have an antinode at this end and an antinode at this end. Again, we're going to say that the length between the ends is L. Well, if this is like the equilibrium line where the string would be if no wave was moving through it, then this end has to have an antinode at it, and so does the other end. But you can't just draw it straight, because that's not a wave traveling through the medium. So it's got to start out up here, it's got to go through a node, and then it's got to hit down here. So that's one extreme of the oscillation, and the other extreme would be like this. And again, this is absurd because you couldn't really build this. I mean, maybe you could if there was no gravity and you attached an oscillator to the middle and the oscillator went up and down, and then you found just the right frequency. But like again, that's fairly absurd. But we can draw the patterns and talk about the relationship, and then when we get to air columns, this scenario will be useful to explain some instruments. So the next simplest pattern would be if there were 2 nodes in the middle. So start with an antinode, go through a node, end with an antinode. There's a node. There's a node. The other extreme would look like this. The next simplest pattern would be 3 nodes out in the middle, and then I think you get it from here. All right. So what antinode, node, antinode, node, antinode, node, antinode. What would the relationship between the wavelength and the length between the ends be here? If you imagine drawing the full wave pattern, it helps to come up with how far this is. So really, let's say it starts here, it goes up, goes down, and then it goes back up. So this would be the full wave. How much of the wave are we looking at from here to here? That is 1/2 of the wave. So go back to my green pen. 1/2 of the wavelength equals L. Okay, what about this one? You start at a crest, you go down, and you end at a crest. Oh, that's a full wave pattern. So that's 2/2, or 1 wavelength is L. What about this one? Here's a crest, here's the next crest, so that's 1 full wave pattern. And then this is the same thing we looked at right here, so that's a 1/2 a wave. So that's 1 plus a 1/2, so 3/2 lambda. Look, it's going up by 1. We've seen this one already. if we put n over 2 times lambda equals L and then solve this for lambda, we get 2L over n, where n is 1, 2, 3, dot, dot, dot. This is the same scenario as 2 fixed ends, which simplifies. There's not a third formula you have to remember. So the formula you end up with if both ends are free is the same relationship that you get if both ends are fixed. So really the only odd one out is when one end is fixed and one end is free. They are odd. I said odd one out. That was a good one. Okay. So I had mentioned columns of air earlier. Being able to visualize the standing wave patterns on strings really helps you understand what's going on in wind instruments, or instruments that use air to create standing wave sound waves, standing sound waves. So the visualization, like right here, is great because it lets you come up with a formula. But there's not a string in here. If there were sound waves entering this tube, there's no string, and the waves are not transverse going back and forth like this. In reality, there's sound waves, and they're longitudinal, and there's a bunch of air molecules in here experiencing compressions. But it's really hard to visualize compressions, and it's really hard to visualize standing longitudinal waves. So often you'll see diagrams where people just sketch a string and go from there. And so you can get all the math right by visualizing the standing wave patterns in a column of air as if they were strings. And so if you draw it like this, the analogy is at this end the string is moving up and down a lot, so that's an antinode. That's analogous to the motion of the air molecules. If the air molecules at the free end are moving back and forth a lot, then that's an antinode of air molecule displacement. And then if there's a node over here, that means the air molecules are not moving very much because there's a closed end right here that they can't move any further to the left, so they're stuck in place. So that one way to describe standing waves in air is in terms of the displacements of the molecules. But if you go further in music theory or sound engineering, you don't really describe standing wave patterns in terms of displacements of molecules. Sound waves are much better described using pressure and thinking about them as pressure waves and measuring the changes in pressure to describe what's going on with the wave. We don't do that as much in IB physics. I think it's easier to understand and explain what's going on if you talk about the displacements of the molecules instead of the pressures. But, well, I'm getting ahead of myself. Let's compare these diagrams. The first one right here, the simplest one, equates to, at one moment, all the air molecules moving to the right. And so right here, they don't have very much displacement, and at the end, they have a lot of displacement. That's the same as if the string were going up. And then the other extreme, where the string's going down, would look like this. The air molecules moving far to the left at this end, and then moving slightly to the left at this end. So that's the simplest standing wave pattern for sound waves in a tube where one end is... Here we talk about the ends being closed or open instead of fixed and free, but fixed is the same thing as closed for us, and open is the same thing as free when you're trying to make the analogy between strings and air columns in a pipe. The next pattern, there's a node here, and so that would be right here. There's a node. And so at that spot, the air molecules aren't moving at all. And the farther away you get from that spot, they're moving a lot, and then there's another node here where they're not moving very much. And there's an antinode at the end. So this corresponds to this. Same thing here. Now there's two nodes in the middle of the pipe. One node, two nodes. And so really this is really what's happening, but it's a lot easier to visualize and draw the patterns if you think about them as strings, like up here. Okay, back to pressure. for a second. The other complicated aspect about describing standing waves in terms of the pressure is that the analogy is reversed. It's a little confusing. If you're describing the sound wave in terms of pressure, so here's a closed tube where the other end, this end, is open and it's exposed to the atmosphere. Well, the atmosphere basically fixes the pressure at this end. This end will always have a pressure which is equal to the atmospheric pressure. You can't change it. Whatever's going on in this tube is not enough to change the pressure of the entire atmosphere. So it flips. It makes, if you're talking about these in terms of pressure, the node is at this end. It's a pressure node. The pressure's not changing. And the further you get in the pipe, it's easier to change the pressure because you're farther away from the atmosphere. So the pressure at the closed end is what fluctuates between two extremes, a high and a low pressure. So it's not that bad. You just flip all the patterns from up here. Here the displacement node was at the closed end and the displacement antinode was at the open end. Well, if you want to describe it in terms of pressure, you flip it. The pressure node is at the open end and the pressure antinode is at the closed end. So it's not too crazy to go back and forth between displacement and pressure, but when you're drawing these patterns for air columns, you have to know if you're drawing them for displacement or pressure because it literally flips where the nodes and the antinodes are. I think that's all for today. Toodles.